Hello and welcome to another Monday Night Calculus. My name is Curtis Brown and I am joined again by Steve Kokoska and Tom Dick. Really excited to have you both here this evening sharing your expertise. Tonight we're talking about motion. So I'm glad I brought my Dramamine. I hope that I'm able to keep things stable among the two of you and hopefully can manage the chat real well. Teachers, I'm really excited that you are here. Students, I'm very excited to have you join us this evening. Please make sure that as you have comments or chat questions, go ahead and post those into the chat box there, and I'll respond to those or pass them on to Tom and Steve as necessary. Also, stick around towards the end of the session. I'll be making sure to post my email address in here for teachers. You can get teacher professional development hours. And then finally, be looking for the teacher document, the answer document. Steve's going to send that to me here tomorrow morning. I'll make sure to post that up on the description. I apologize for not getting the questions out until this morning. Wanda Burns called me on that over the Thanksgiving break, and so I apologize. I didn't get those out there. So if you were trying to do your homework and couldn't, you can always blame it on, hey, the guy from Texas Instruments didn't post my homework, so I couldn't do it. All right. So I think that gets us going. Steve or Tom, who's going first tonight?
I'm going to post a question first.
All right. You pose the question, Steve, and then we'll pass it over to Tom.
The more important question, Curtis, about the problems is, did you do your homework for this evening?
Well, see, what had happened was I didn't do my homework either because I forgot to post them onto the website.
Well,
so I'll be winging it just like usual, and so hopefully I can keep up. But right. I know I can count on Wanda and Mark, Dawn, and some of these others to keep me honest and to answer questions as you pose them.
All right, very cool. We've got some cool, I think, some neat particle motion problems this evening, some that use technology, some we're going to solve analytically. Some typical problems I think that you might find on the AP exam, especially on the free response portion. We've got a couple of challenge questions in here, and we've even got a couple of overtime questions if we have a little bit of time towards the end to get to them. So the first problem, we're going to do this a little differently tonight, Curtis. Tom is actually going to try to explore the first problem using technology. And then we'll come back over to me, and I'm going to try to solve it analytically. So the first problem involves a particle moving along a straight line. And we have the velocity of this particle given at time t as v of t is the square root of 2 cosine t over 2 minus 1. The position of the particle is given by this function s. And we know that the particle is at position 6 at time t equals 0. We have various questions about this setup. First one is about when is the particle moving to the left, find the position, find the total distance between the particle's positioned a couple of times, and so forth. So, Tom, you're going to take a look at some of these via technology, and then it'll come back to me?
Sounds good, Steve.
Okay, here we go. I'll stop sharing and hand it over to you.
Okay. All right. Okay, so let me give this a shot. Hopefully we'll get this to work.
You're going to be using the 84 first, Tom?
Yes. Yeah, I'll use the 84. I know you have some stuff with the Nspire that you...
I do indeed.
So, all right, so... pardon my... I think I'm getting a share screen up here.
Okay.
There we go. And
there we go. Now great. I see it coming on.
All right. Sorry for the little bit of delay there. So, so we're going to take a look at this using technology. Now, the problem that Steve posed, he chose a function for the velocity of this particle that one can work with paper and pencil. It's all the calculations you can do. It turns out that the kinds of questions being asked here, they're going to involve looking at the graph of the velocity for interpretations, calculating derivatives of velocity in the case of finding acceleration, taking integrals of velocity, definite integrals to find changes in positions or distance traveled. And all of those are things when on the calculator open part of the exam are really typical types of problems. And so that's why we thought we'd dive in this, and we're going to treat this as if it was on the calculator open part of the exam, even though the function Steve chose is one could see on a paper and pencil part of the exam. So I'm going to just jump into the y equals menu and go ahead and enter in y1 the function that Steve gave as the velocity. And so I believe that was the square root of 2.
Right.
And that was times the cosine of, now I'm going to use the independent variable x because I'm in the function mode here. So, so x is going to be time for us. And so x over 2. And then close off parenthesis, and then there was finally a -1 as part of that. So that's our velocity. And the first question that was posed here had to do was, when is the particle moving to the left? And so right off the bat, we need to interpret, okay, what's that going to mean? If we're given the velocity, how would that tell us when the particle's moving to the left or to the right? Okay, so this is moving on a horizontal line, and so we're the assumption here is on the number line, moving to the left is moving toward the negative direction, and moving to the right is the positive direction. So we're looking for, where is this velocity negative? So let's go ahead and graph. Before we do that, let's go ahead and get to the window and set that up to be something reasonable here. I think it was from 0 to 20 was the interval.
Right.
So I'm going to give us a little bit of room to the left and put in -5 for my x-min. And then I'll put in 20 for my x-max. And I think the y-scale is probably okay. So let's take a look at the graph of this and see what we get here. All right, there's the graph of the velocity function. And just a note to teachers out there, taught calculus lots of years, and I got to a point where when I was doing what we call rectilinear motion, that's motion along a straight line, I've tended to start with motion along a vertical line. And the reason I've done that is because the translation between the motion of the particle or the object and the sign, you see what the sign of the velocity is given by the y coordinate of the velocity function. And so that interpretation is a little bit more direct with a vertical line. So here, when the velocity is negative, or the velocity graphs below the horizontal axis, that's when the object's moving to the left. And when it's above the axis, that's when it's moving to the right. So I'm having to do that kind of shift between the vertical orientation of the graph and the horizontal motion of the thing I'm really trying to interpret is a kind of extra layer that I have to be careful about. So where are these points? Well, it looks like there's some point between between 1 and 2 is where it changes from positive to negative. So we want to kind of pinpoint that. And we can see over here, it looks like at exactly, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks like at exactly 11 and 14 are the other two times. I'm just pausing there to see if anybody will complain, because if you take a look at our function here, let me go ahead and turn on the trace. It's pretty unlikely that this function's equal to 0 at exactly 11 and 14. Okay. So but those values are close. So I'm going to go ahead and trace, since I've got the trace turned on. Let's see, the first value was somewhere between 1 and 2. So let me just jump over to 1. Now, when you're tracing, if you just type in a number, like 1, and hit enter, it's going to jump to that value right away. There we go. So now we're pretty close. And as I trace here, okay, I see a change in sign. So it's somewhere between 1.4 something and 1.6. So if we want to pinpoint that, let's go ahead and do the calculator. And we want to calculate the 0. And left bound, let me just back up a little bit to where it was positive. I'll hit enter there. And then a right bound, I'll just need to move a little bit to the right. Hit enter there. You can see I'm giving it a very narrow interval. Should be good. I'll go ahead and enter that as my guess. And as I mentioned, Steve chose a function here where we could actually solve this by hand. I've gone ahead and used the calculator here. And where you see where that 0 is, you might recognize that number, the 1.5707. Okay. Be pretty sure that's probably pi over 2. All right. And if we check that out, if we plugged in pi over 2 into this expression up here, we could see that, yes, indeed, that's exactly where it's equal to 0. So it's a precise. Okay. The other two zeros, let's see, I said there was one that looked like at exactly 11. Let me type in 11 here. Jump over to that. It was pretty close, but the y value is not quite 0. Okay. But it's awfully darn close to 0. And so we could do another 0 calculation here. I'll just go ahead and let you know this turns out to be 3.5 pi, 3.5 times pi, or 7/2 pi. And this one is 9/2 pi. And again, you can try those out and see that those are exactly the solution. So that's where so one of the intervals where it's moving left would be between time t equals pi over 2 and time t equals 7 pi over 2. And then the other interval where it's moving to the left is between 9 pi over 2 and 20. So those would be those two intervals. I'm going to jump around a little bit here on the parts of the question. I'm going to quit this. We've got that in Y1. The part E on this question actually asked for the acceleration of the particle at time t equal pi. Well, in order to do that, we need to know, well, the acceleration is going to be the derivative of velocity. So if I want to calculate that, so I'm going to try to calculate the acceleration at time t equals pi. I can go to my math menu. I think, let's see. Excuse me, I thought I'd pressed it. Being a little sluggish here, my apologies. There we go. And let me pick up number 8, the numerical derivative. There we go. And we'll take the derivative. Remember, for us, x is time. And we can now just pull out, oops, let's see, I think, there we go. We get back inside those parentheses. Okay, so I'll pull up Y1. And we're going to evaluate that at time x equal pi.
Yep, that's correct.
And there we go. And when you get used to working with these functions, especially the trigonometric functions, you might look at that and say, the number looks familiar. Okay, it looks a bit like the negative square root of 2 over 2, might be. That sound right, Steve? I don't know. think it is.
Good.
All right.
Very good.
All right. And before I turn it back over to Steve for him to look at, let me do one other calculation here. Let's say we wanted to know the position of the particle at time t equal 2 pi. Okay, for us it'll be x. Okay, so we were given an initial position of 6 at time 0. So let's go ahead and put in that value 6, because we're starting out at that point. And then we'll be integrating the velocity to get the change in position. Velocity is rate of change of position. And so the integral of velocity will give us a total change in position. So now I'll do a math menu again. Get my FN int. We'll integrate from 0 up to 2 pi. I hit an extra 2 there, so let me back up and put in a pi there instead. There we go. So I think we have 0 to 2 pi, and this time we'll just be integrating velocity. And we're using x here. Okay. And so this should give us then the position of the particle at time equals 2 pi. Okay. Most common mistake students might make is forgetting that initial position, because the integral is just giving us the change in position, and so we needed to know that starting point. And so, Steve, I'm going to turn it back to you, and then when you're done with the analytic thing, I did want to take a look at using parametric mode to actually graph this position function. Okay?
Okay.
All right, so let me do the stop share at this point and bring it back over to Steve.
Sounds good. All right, great, John. So let's take a look at this problem now a little bit more analytically, although I am going to show a little or a couple of graphs that I've created with Mathematica. I'm going to go back up here to the top of this question and just remind myself of a couple of things that I'll need as I solve this one. That's over here. That is at a time t equals 0. The position of the particle is 6, so I'm going to write it like that. And now as I think about part A, when is the particle moving to the left? Tom alluded to this and said, well, what we really need to do is we need to find out, when is that velocity less than 0? When is that velocity negative? That indicates that the particle is moving to the left. So I'm just thinking about this out loud and how I might solve this. And I'm just going to scribble a little bit off to the side. For me, that means, well, I'm going to have to find the places where v of t is equal to 0. Those values of t are going to divide up that interval, 0 to 20, into subintervals. And I'm going to put a little arrow here because I'm going to use a sign chart. And I know a lot of people don't use those anymore. They are not acceptable justifications on the exam. But I still think this is very nice mathematical notation. It's certainly acceptable to use. It's just not sufficient justification on the exam. So let's see how we might attack this analytically. First thing I'm going to do is I'm going to take this velocity function v of t, I'm going to set it equal to 0. I'm going to bring the 1 over to the right-hand side. I'm going to divide by the square root of 2. And I've got to solve this expression for t. So I'm going to think about, well, when is that argument equal to, or what does that argument have to be equal to in order for the cosine to be 1 over the square root of 2 or the square root of 2 over 2? So I thought about that a little bit, and there are two cases here. The argument t over 2 could be pi over 4 plus 2n pi, or it could be 7 pi over 4 plus 2n pi. Now, skipping a little bit here because of time, I had to think a little bit about this. And to think about, figure out what are the values of n that will return values of t in that interval 0 to 20. So I tried a few over here, and I found those three values that Tom found graphically, that Tom found numerically. And there they are analytically, pi over 2, 9 pi over 2, and 7 pi over 2. So what I did next is I created a sign chart. My interval is 0 to 20, and I tried to draw this sort of to scale here. I put tick marks corresponding to the times when the velocity is 0. And then I need to figure out here, without drawing a graph, I need to figure out, well, what's the sign of the velocity in those subintervals? And we all have our own ways of doing this. Some of us pick specific values in each interval. Some of us argue sort of in general. But this is what I got. In this interval, it's positive, negative, positive, negative. If you think back to Tom's graph, I think you'll remember that that agrees. So that allows me to draw a conclusion here. If I can arrow down just a little bit. The particle is indeed moving left when v of t is less than 0, and that occurs over these intervals, pi over 2 to 7 pi over 2, and 9 pi over 2 to 20. Here's a similar graph that Tom produced. I did that one with Mathematica, put in a couple of extra tick marks to make that easier for me to understand. And just so that we all understand each other, just so that we're all on the same page, if you were solving a problem like this on the exam, you can certainly include this. You can certainly include a sign chart, but that's not enough. You'd have to say something like this. And in fact, that circled part right there is all you really need without the sign chart. Now, for me, and we've kidded about this frequently, how would you be able to make that statement that's circled without having some sort of sign chart or graph in front of you? Not sure. Wow, all of that, I think we're done with part A, Tom. Here's part B, analytically. Let's see if I can find the position of the particle at time t equal 2 pi and t equal 5 pi. I won't go through everything in gory detail, excuse me, but I do want to remind you, Curtis, I think you and I have talked about this before. I always think about this as kind of a fundamental theorem of calculus problem, really. You might start out by saying, well, I know that the definite integral from 0 to 2 pi of v of t dt is equal to, well, the integral of the velocity is the position function. So I've got to evaluate that at the upper bound, s of 2 pi minus s of 0. And what I really want here is the position of the particle at 2 pi. So I solve for that. I bring this to the other side, and I've got s of 0 plus that definite integral. So that is another way to think about it. One way is to think about it with a fundamental theorem of calculus like this. Another is to say, well, it's the initial position, the position at time 0, plus the change in position, that definite integral 0 to 2 pi. Well, okay, analytically, here's the velocity function. There's the 6, s of 0. Here's the velocity function. In order to integrate that, well, I don't want to say it's simple, but it is a u substitution. I won't go through that in detail, but that would be a u equal to t over 2. I guess I need a 1/2 out in front, so I'd have to multiply by 1 in a convenient form, 2 times 1/2. So that's why there's an extra 2 out here. And don't forget, we've got to integrate or find an antiderivative of 1. That's just t. And now I evaluate. I plug in the 2 pi, I plug in the 0. And let's see if I've done everything correctly. Let's see, did I get this? The sine of pi, well, let's see, that's going to be 0. Sine of 0 is just plain old 0. And let's see, did I get this? Yes, 6 minus 2 pi. There we go. Let's think about this just for a second. Tom had the position of very close to 0, didn't he? A minus a negative 0.03, I think. Does that sound right? Yeah, I think so, because 2 times pi would be 2 times roughly 3.14, a little bit bigger than 6. So 6 minus that is going to give me just a small negative number. So I feel pretty good about that. All right, So for the next one, we're going to go through the same sort of calculation, but this time we have to go 0 to 5 pi. So there's the velocity. The upper bound this time is 5 pi. Same antiderivative. Plug in and evaluate. Well, let's see. This time that's still 0. That's 0. But the sine of 5 pi over 2, that's going to be equal to 1. So there's the analytical expression. Got to think a little bit about that to figure out, to determine whether or not that's negative or positive. And here's something that Tom may get to with technology, but I was actually able to, from the velocity function, and from that initial position at 0, I was actually able to graph this position function. Here's the position of the particle at time 2 pi, just below that t-axis, just barely negative. Here's the position at 5 pi. Well, that's a little bit bigger than -6 here. Cool. All right, Curtis, be on your toes here. I've got a couple of questions coming up for you.
All right, I'll do the best I can.
All right, find the distance between the particle's position at t equal 3 pi and t equal 4 pi. Now, there are a couple of ways we might be able to do this. Whoops, I'm sorry, I went a little bit too far on that one. Here's how I'm going to try this. I'm going to start out by taking a look at the displacement here. The definite integral from 3 pi to 4 pi, the integrand there is v of t. And we've done this antiderivative a couple of times now. So there it is. There's the t on the end. I'm going to plug in my 4 pi and my 3 pi, and I did a little bit of simplification in the arguments. And I ended up with a 2 square roots of 2 minus pi. Now, that's not the answer. It says find the distance between the particle's position. And so what I needed to think about is that value, 2 square roots of 2 minus pi, is that negative or positive? And perhaps I couldn't quite tell by looking at it symbolically. So I converted it to a decimal and recognized, well, it's negative. So that means that the particle ends up to the left of where it is at 3 pi. At 4 pi, it's a little bit over here to the left. And so that means that the distance, which is a positive value, is the absolute value of that expression.
Right.
Which would be pi minus 2 square roots of 2. That's a nice problem.
It is.
Now, in thinking about this, Tom and I were talking about this problem. Here's a sort of an open question, Curtis, and see if anybody will get an answer to this in the chat. Can you explain, let me back up just a little bit, in the context of a particle motion problem, can you explain the difference between those two expressions? We'll kind of leave that as an open question for a bit and see if anybody puts anything in the chat.
Yeah, I'll be really curious to see what people put in the chat. Of course, the first one is the distance you were asking for, right? The physical distance between two objects.
Very good. Excellent.
I'll be curious to see what folks talk about on the second one. Although you've now kind of helped us out
giving it away
bit
yes,
by going to part D here. So
it's a good problem because students often confuse that on the exam, in all honesty, Curtis.
Yeah.
Some we get absolute values in a lot of different places. It's important, I think, to remember the difference between those two, where those absolute values belong, and which type of problem. In this one, in part D, we want to find the distance traveled between 0 and 2 pi. And this is a definite integral from 0 to 2 pi of the absolute value of the TDT. But wait a minute.
We did get a couple of people respond talking about the magnitude of displacement.
Well, that's a good phrase. I like that.
Versus the length of the distance traveled, or the total distance traveled. So I think, the idea of what is the magnitude of displacement
That's
versus
very
the
good.
total
Thinking of
distance
it as a
traveled.
vector. That's very good. I like that. Yeah.
Because you can do total distance traveled around in, well, I guess back and forth. If you go back and forth to the store 5 times, total distance traveled isn't 0.
All right. Well, how
All
do I
right.
do this one? How do I do this one? I remember my college prof always telling me that when you ever have a problem with an absolute value, somehow you've got to work to get rid of that absolute value before you do any calculus. And so I may have skipped a step or two here, but what I really needed to think about was, where is that argument positive and where is it negative? And so I've got to think back a little bit, maybe to my sign chart, or to how we answered part A. And if you remember, the velocity was positive between 0 and pi over 2. Between pi over 2 and 2 pi, a little bit beyond, it was actually negative. And so, if I take the absolute value between 0 and 2 pi, it's just that expression, v of t. But if I take the absolute value of v of t between pi over 2 and 2 pi, it's minus v of t, because this argument is negative. That's the definition of absolute value. And that's why there's an extra negative sign there. Okay, some repetition here. Same sort of antiderivative. We've got to do a lot of evaluation here. Yeah, there's a lot of analytical stuff to do. And I ended up with a 4 plus pi. Cool. So the toughest part of this problem may be in this very first step, to recognize, to remember, to understand how to split that up into 2 separate definite integrals. Very good. And in part E here, let's see if we can find the acceleration of the particle at time t equal pi. And I'd like to know, is the particle speeding up or slowing down at this time t equal pi? Well, I apologize for this, Curtis. I may have done this a little bit out of order, but I started out by finding or evaluating the velocity function at pi. So I just plugged in a t equal to pi, there it is, and I did a little bit of evaluation. Let's see, that's 0. So this is just minus 1. And I noted that that was less than 0 because I think I'm going to need that observation as I try to determine whether or not the particle is speeding up or slowing down at this time. In order to evaluate the acceleration, let's see, I've got to take the derivative of the velocity. Well, let's see, I've got to use the chain rule here. Here's the square root of 2 constant out in front. Derivative of the cosine is minus the sine. Derivative of the inner function is 1/2. And a little bit of simplification. To find the acceleration at pi, I'm going to plug in a t equal pi, and I did a little bit of evaluation. There's a minus square root of 2 over 2, and I noticed that that was less than 0 also. Let's see if I got all the answers here. I've got the acceleration at pi, there it is. Now, is the particle speeding up or slowing down? Well, let's see. Both the velocity and the acceleration are negative and therefore have the same sign, and therefore the particle is speeding up at time t equal pi. I don't know if I've ever really looked at this, but I thought it might be interesting to consider the graph of v as Tom presented earlier. And here's the point on the graph where t is equal to pi. And I was wondering if there's any way to look at this graph of the velocity and determine whether the particle is speeding up or slowing down. And we'll leave that as sort of an open question. And Tom may have the opportunity to do this with technology, but I'll just remind you, if you don't, Tom, that's fine. I saw this on the, student reported this on the exam a couple of years ago, and I had not thought about this. This is something that technology will do for us. If we want to know whether the particle is speeding up or slowing down, really what we want to do is we want to take the derivative of the speed, and we want to know whether that's positive or negative. It's positive, particle speeding up. Its speed is increasing. Negative, slowing down. So it is possible, I believe, on a calculator to take this kind of a derivative and answer this question. Oh, okay, and evaluate it, let's say, at t equal pi. So let's see, anybody got an answer to this one, Curtis? Can you use the graph to determine whether or not the particle's speeding up or slowing down?
I haven't heard anyone say how they would use the graph, or I shouldn't say heard, read in the chat anyone saying how they would use the graph. But I was thinking about it, and I was thinking about, if I'm looking at the graph to think about how this particle may be speeding up or slowing down, my question would be, is that velocity graph getting closer to zero or further away from zero in either direction? In other words, if the velocity graph happens to be positive, but approaching zero or coming down towards zero as time is moving on, then I would say the particle is slowing down. Likewise, if the particle, if the velocity were on the negative side, but increasing and going closer to zero, I would also say the particle is slowing down. The key word there is speed, right? We're not asking if the velocity is increasing or decreasing. We're asking if it is speeding up or slowing down, right? So we're looking at the absolute value.
I like your interpretation. I'm going to give you another one to think about. When I look at that graph and I look at the position of the particle at time t equal pi, here's one thing I notice right off the bat. I see that v of pi is less than zero. Is there anything else you can tell about that velocity graph at that time? Is there anything else screaming out at you? How about if I draw a line in like this? That's a perfectly straight line.
That's a perfectly straight line. Are you talking about the slope of that line and wanting me to give you that the slope of that line is negative and the velocity happens to be negative, therefore?
It is speeding up. Very good.
Speeding up.
Very good. How about that? That's kind of cool. So there's a couple of different ways to look at this problem. One graphically, one with technology that we couldn't do actually 25 years ago. How about that? All right, Tom, take a quick look at 2 before I turn it over to you for 84 technology. Is that all right? I'll take that as a yes. All right. So here we go. We have a
Tom's still on mute, so he wasn't going to be able to talk to you anyway.
All right. This time we have another particle moving along a straight line, and this time the velocity particle is given by this more complicated expression. It's got a trig function in it. It's got an exponential function in it. We know that the position of the particle is given by s of t, and I'm going to tell you that it is continuous and differentiable. T is measured in seconds, s is measured in feet. We know that s of 0 is -1, first thing. Can we find all the values of t for which the speed of the particle is exactly 1? Well, the very first thing I thought about is how would I solve this analytically? And so what I really need to know is, when is the speed, the absolute value of the velocity, there it is with the expression that we're given, when is that equal to 1? Well, I looked at that initially, I thought, jeepers, I don't know if I'm going to be able to solve that analytically, but we'll come back to that in a minute. So I'm going to graph this. I'm going to graph the velocity function. Now, I could graph the absolute value, but this is the way I chose to do it. I'm going to graph the velocity function, and I'm going to graph plus or minus 1. And I'm going to try to figure out where those curves intersect. So this is what the TI-Nspire. If you can see color here, the velocity curve is in blue, and my 2 horizontal lines at 1 and -1 are in green. And I found some points of intersection right there and right there. And it looks like the speed of the particle is exactly 1 at about 3.850 and 5.196. Now, it turns out that the TI-Nspire CAS version will even solve some of this analytically for me, which is very cool. So I define the velocity function, and then I can use the solve function And it's kind of hard to see, but in between here, or right after that solve function, where I say solve the absolute value of v of t equal to 1 for t, is a little vertical bar, which I read as such that. So solve that expression such that t is between 0 and 6. And it came back with those two analytical expressions for t, which is very cool. And just to double check, to make sure what I found over there on the graph screen was correct, I did the exact same expression, but this time, again, kind of hard to see, but I said set that equal to 1 with a decimal after it, so that now even the CAS version will come back and give me a decimal approximation. And yeah, that's what I got over there on the graph screen. Curtis, I'm wondering about this. Maybe you can help me a little. I'm going to try my best here to arrow down a little. This was working a little bit better earlier. Suppose I wanted to solve this expression analytically. Do you have any idea on how I might do that? And I'll give you a hint. I've got to take that expression. I've got to take that expression that's inside the absolute value and set it equal to 1, set it equal to -1 separately. So let's take this first. We won't do the whole thing, but let's take 2 times the sine of v to the t over 4 and set that equal to 1. Is there any hope for us to solve that analytically? Oh, wait a minute. I'll do the hard part. Sine of
Or you'll go ahead and
is equal to 1/2. Any ideas what we might be able to do here?
And then subtract.
No, we're not going to subtract anything.
When sine might equal 0. Man, I don't know, Steve.
No.
Making me think tonight.
Well, how do we sort of get rid of that sign out in front there? We have to take the...
Or you can arc sine, yeah.
There you go. Now, be careful, Curtis. Be careful. If you take the arc sine of both sides, on the left-hand side, you get e to the t over 4. I'll write it in, just for the heck of it.
Yeah, write it in for me.
What do you get on the right-hand side? Think about that a little bit.
Sine of a half. Oh, geez. Somebody give me a unit circle. Help me out. I don't have that memorized anymore.
What do you get?
One of my students.
Well, if you think about the unit circle, I believe that
5 over 6, 5 pi over 6, something like that.
Well, it's not going to give me 2 values. It's going to give me pi over 6.
I'll take that one.
Okay.
Take log base e.
Very good.
Log.
And that's t over 4. And if I think about this just a little bit, help me here, Curtis. Pi is 3.14 divided by 6.
Yeah.
This value is less than
1. Yeah. So it's going to be negative.
This expression is negative.
Yeah.
Yeah, that's not.
I haven't even got there.
So we'll leave this as sort of an open question here about how we actually solve this analytically. But if I just sort of follow my intuition here, that leads me to an incorrect solution. So you got to think a little bit more carefully about that. Cool question. B, find the position of the particle at time t equal 5 seconds. Okay. So again, we've seen a couple of problems like this already. S of 5 would be the starting point, S of 0, plus this definite integral, the change in position from 0 to 5. At 0, it was at -1. I don't think I have much hope of actually integrating that analytically, so I plugged that into my calculator. I got a 6.104 roughly. And just to double check this, I graphed both the velocity function and I was able to graph the position function here. And you might do this and think about, try to explain the relationships between the two graphs. Is the position actually increasing when the velocity is positive, and vice versa? Is the position decreasing when the velocity is negative? Find all the times t at which the particle, between 0 and 10, which the particle changes direction. Well, all right, I drew a graph of this. Tom did something like this with the other problem, with the earlier problem. Here's a graph of the velocity. I found the points of intersection. And yes, indeed, there are 3 places between 0 and 10 where the particle changes direction, where the velocity goes from negative to positive or positive to negative. That's a nice technology active question. And is the speed of the particle increasing or decreasing at time t equal 4? Well, let's see. Tom alluded to this. Here's v of 4. Here's the derivative of v at 4. So that's actually computing the acceleration at 4. That's negative. The velocity is positive, so the signs are different. So the speed of the particle is decreasing at time t equal 4. And I did the same sort of thing here, Curtis. Here's a graph of the velocity. There's the position, pardon me, there's the value of the velocity at time t equal 4. So let's see, the velocity is positive there. And if you take a look at the slope, that's negative, differing signs. The speed of the particle is decreasing.
It's decreasing, right?
And one more, find the total distance traveled by the particle over this definite interval. Very easy here using technology. This is a nice problem for me to remind you that when you take the exam, when your students take the exam, remember that they must present the mathematical setup and then go to your calculator. It seems to me that in a lot of these problems, there isn't much required at all. On this kind of a problem, all you'd have to do is to present this right here. To present the mathematical setup, go to your calculator, get an answer of 6.749 and report that, and you would get full credit for that answer. Cool. I have a hot air balloon problem, but Tom, you're going to do a little bit with technology?
Yeah. Let's see. Am I off mute here?
Nope, you're good.
Okay. All right. Yeah. Just let me show a quick thing here, Steve.
Okay.
And I'll get a share going here. And so I just wanted to show how someone might work with the actual parametric plotter. It actually makes sense to do that with particle motion.
Okay.
A lot of people think of the parametric plotting as for plotting curves in the plane. So that's a BC topic. But you can use it for just a motion along a line, and just want to illustrate how you might want to approach that. First of all, let me just kind of back off of this just a little bit and point out that in doing that, you'd want to go to your mode menu. And when you get there, you'll want to go down and change from function to parametric. Okay. And then once we've entered parametric mode, a lot of things happen to the calculator to kind of optimize it for that. You go to your y equals menu. You'll see pairs of functions for both x and y in terms of t. And I've gone ahead and taken the liberty of setting up what would be the actual position function for this particular problem that you were just looking at, Steve.
Okay.
And so I just want to kind of deconstruct that so people can see what was entailed. To get it up off the x-axis, I'm assuming this is moving along a horizontal line, but I'm putting the horizontal line at y equals 1. And so that's why I have y1t here, just equal to the constant 1. So the particle will be moving horizontally, but it'll be up along the line y equals 1. So the x-coordinate of the particle, and that's where all the action takes place, the -1 here, that was your initial position. I think you said that the s of 0 was equal to -1. And then notice here I've got an integral function. It's integrating from 0 to t, and this was the velocity that you gave. And so this will give us the change in position between time 0 and time t.
Mm-hmm.
So this will actually be a position function that we could actually plot. Okay. Now, if I go to the window to set this up, just a reminder to folks that when you're parametric plotting, your t interval is something you're going to need to set in your window. I put the minimum value for t is 0, and I just chose t equal 10 for my maximum value. And I'm going to step in increments of 0.05. And my Ymin, Ymax are and Xmin, Xmax. These are actually kind of your typical just zoom decimal values here. So let's go ahead and take a look at what the graph of this looks like. And this here is a completed graph. So I'll tell you what, I'm going to go back to the window just so people can see it plotting. I'll change my T max to 12. And then regraph. So you can see it graphing from the get-go. And let's see, there it goes. It's moving along. See, now for each of those values, it's calculating that initial position of -1. Notice that it started out at x equal -1. And now thing is, we can't really see where it's turned around. So we might want to trace it to see that. Or there's another alternative. I think you might remind me of this, Curtis, the way we can get that dot kind of plot for this.
Yeah, I was going to speak up, but I wanted to let you show it. I do notice that it's still graphing.
Still graphing, yeah. And it's graphing because every value that it's graphing it's calculating one of those definite integral values. So it's going to be kind of slow, but one can kind of see that
whenever you plotted from 0 to 12, how that was going to.
I should have used.
One thing you can do. One thing you can do, Tom, and I love this for demonstrating it. Yes, I do know that the trace works really nice for demonstrating that moving through time. But if you go back to y equals and arrow to the left and highlight all the way over to the left where you highlight the color and the type of line that it draws. If you hit enter on that, and then you go down, there's the option for line. So arrow down to where you highlight the little toggle for line. And if you left arrow, actually it's faster if you go left arrow. There's this little line with a circle on it. Whoops, you passed it there.
Oh, Dave. Sorry.
That's all right. So there's a little line with a circle on it, and you can watch that little. So what that will do, and there's two options. There's one where there's just the little circle without a line on it, and then there's an option with the line and the circle. If you choose the one with the line and the circle, it actually leaves a path wherever it goes, so you kind of see the places that the graph has been. But that little particle looks like a particle. So go ahead and hit OK.
All right. And I'm going to go ahead and change my window.
Well, just by changing that, it'll actually force a regraph. But
well, I realized the interval that was really 0 to 6.
Oh, it was? Okay. So let's just do 0 to 6 then. And
just to move things along, I'm going to change the t step to a larger value here.
Maybe a 10th. Would a 10th be good enough?
Let's try 0.2 and see what happens.
Okay. 2/10, that's fine.
All right. Let's try the graph now. Oh, nice. So we can see it moving. That was fairly quick, actually.
That was, yeah, that's why I was like, well, do we really want to do that?
We can go back to the window and change that back to
maybe 0.05 or even a 10th.
0.05, okay.
But the idea is that you get to see that little dot move along and show that over time. It's sort of like a little animated, hey, this is what our graph is doing. You can kind of see it slowing down then moving back to the left.
Starting to turn back. Yeah.
Mm-hmm. 0 to 6 doesn't get you very many iterations there. So.
Right. But it's great for illustrating the difference between just a simple change in position and the actual total distance traveled too, because
right,
it's retracing where it's been before, you're racking up more total distance traveled, even though now the total change in position may be decreasing from what it was originally. So
right.
Okay, great. Thank you for this. Appreciate that. Yeah, I'm going to stop and share so Steve can get to this graphical problem, which is a really good one for, it's a really nice AP kind of question.
Thanks, Tom. All right, we probably won't have the opportunity to get through all of this, Curtis, but we'll start it. So this has to do with a hot air balloon ride at a state fair. They often have some of these, a hot air balloon ride at the Bloomsburg State Fair. And let's suppose that it's actually controlled on a rope. And so it moves perfectly vertically, okay? Up and down this rope. Somehow this is tethered. There's a helicopter up there or something. The velocity of the balloon for t between 0 and 38 is modeled by a piecewise linear function, and it's shown in this graph. And at time t equals 0, the balloon is on the ground. So that means that s is equal to 0. So the first thing we'd like to know is, are there any times at which the hot air balloon changes direction? Well, we hope so. We want to see if we can find those because we hope that we'll end up back on the ground. And so we'd have to find those places, thinking a little bit about what we've done in problems number 1 and 2, where the velocity changes sign. So I've got to take a look at my graph here. I don't have an expression for this velocity. This is strictly graphical. Changes direction there because the velocity goes from positive to negative, negative to positive, positive to negative. So there are 3 places where the balloon changes direction. So you can think of it as going up, down a little, up some more, down a lot, finally back to the ground. Find the height of the balloon at time t equal 8 seconds and at 22 seconds. Well, let's see here. This is, as Tom mentioned, kind of a typical sort of a problem where we have to recognize that the definite integral can be interpreted as the area under the curve. And so s of 8 here is just the definite integral from 0 to 8. Wait a minute. What happened to s of 0 in there? S of 0 plus that integral. Well, remember that the balloon started on the ground, that s of 0 was equal to 0. So how do we figure this out here? Well, let's see. The integral from 0 to 8 would be the area underneath that curve from 0 to 8. The velocity is positive. We can picture and feel this balloon rising. And there are a couple of different ways to find this area. And I think what I did is split it up into the area of a triangle and the area of a rectangle. And I got 120 feet. How high up is the balloon after 22 minutes, was it? Well, definite integral from 0 to 22. And I've got to split this up into parts where the velocity is positive, where the velocity is negative. If you can see this color, this is blue over here, where the velocity is positive. Green down here, I'd have to subtract. Blue over here, where I'm going to add again. The balloon is rising. Several different ways to find the areas here. There's some triangles in there. If you look at carefully at some of my calculations, I actually thought about some of these regions as trapezoids and found the area by using the area of a trapezoid, and I ended up with 240. And this is a nice one too. At what time in the interval 0 to 38 is the hot air balloon at its highest, and how high is it at that time? I like to solve these problems by using the candidates test. And so what I'm going to have to do is to find all those places where the velocity is 0 or where the velocity does not exist. So the velocity is 0. We already found those places at 12, 17, and 24. And be careful here. There are some sharp edges in the velocity function, but that means its derivative would not exist there. But the velocity is actually defined everywhere between 0 and 38. So it sounds kind of funny But are there any places where the velocity does not exist? No, there are none. And so what I need to do is to evaluate this expression, 0 to t, v of x dx, for these values, the endpoints, 0 and 38. I could probably rule those out with a sentence, a logical sentence that says, we know that the balloon is on the ground at those 2 times. And I evaluate this integral expression at those 3 times using an area argument. There are my values, and it turns out it's at highest. Let's see, at time t equal 24 seconds. This balloon is really moving, and it's at 270 feet. Find the total distance traveled by the hot air balloon over that interval. Well, again, we have to worry about where is this velocity negative. Another way to think about this is we could actually flip this over the x or over the t-axis. We're going to take the areas, all of these areas, and add them up. I did all of that, skipping ahead a little bit, and ended up with a 590. That's kind of cool. Is the balloon speeding up or slowing down at time t equal 14 seconds? Hey, that's a good question. It's pretty easy to evaluate. Let's see, the velocity at 14. Let's see, I just read off the graph and got a -5. But how did I get that value right there? How did I figure out the acceleration or the derivative of the velocity at 14? Curtis, any chance? How did I get that one?
Sorry, I was posting something in the chat, Steve.
Okay. Well, I have to
I
take
was not listening.
Right? I have to take
Say that again. Oh, Wanda says it's the slope.
Fantastic. She's on your side, Curtis.
She's on my side. I got Wanda on my side. That's great.
So the balloon is indeed speeding up because these 2 signs are the same. We've seen that a couple of times this evening. So I like that problem. That's kind of a neat real world free response type question. And we had a couple of overtime problems that actually dealt with the same kind of concept here. Let me just take a look at one kind of quickly.
It's good you call them overtime problems, Steve, because we're overtime.
Sorry about that.
That's all right. Keep going.
This is simply, how do you find the indefinite integral e to the -1 over x divided by x squared? When I teach this, I talk about something called calculus vision, and you have to think a little bit about this and see that, well, this is going to be a nice u substitution, because if I let u be equal to -1 over x, I've got its derivative as part of that integrand, as part of that integrand product. And again, the way that I like to do this is to actually solve for dx. It's okay for me that this is in terms of x and u. I'm going to take everything from the x world into the u world. There's e to the u over x squared. There's dx. The x squared cancel. And the whole idea behind this is to take something that looks very difficult in the x world and to translate that into something that's very easy in the u world. That's just e to the u plus c. And to finish it off, we go back into the x world. There's the final answer. This one was very similar in that it was a u substitution, and you had to be kind of clever about that. And of course, we'll post these answers tomorrow sometime. Fantastic, Curtis. Excellent. A lot of cool stuff on particle motion. A couple of good overtime problems. Enjoyed that.
I love it.
Thank you.
I did get a question whether Tom gets 1 overtime possession or if it's only Steve that gets overtime possessions. We'll plan for that next time around. Tom, you can have an overtime possession as well. We'll need to install a coin flip here, I think, make sure that this is a fair time afterwards. Well, I just again thank you guys both, Steve and Tom, for putting the time together to put this together. Teachers, don't forget to reach out to me for that certificate. Be happy to send that along to you. I also put in the chat that we'll be talking here in 2 weeks about the FTC. So don't forget to come back and join us. That's our last installment of the year from Monday Night Calculus, and we'll after next week or 2 weeks from now, we'll see you on the other side of January. It's going to be awesome. Looks like we had several students show tonight was fantastic. Continue to encourage teachers to have their students join us. All right, well, we'll sign off here and we'll see you back here in a couple weeks.
Fantastic.
Great.
All right, I think that should do it, guys.